In today's class, we are just going to revisit some of the computer arithmetic algorithms and implementations, which you might have already done a little bit in your VLSI course. Okay. So the first one is like we start with half adder and then we'll build up on a full adder and different types of full adders. So the basic building block is an half adder where you have 2 bits which requires to be added. If I make a K map for that, so 2 bits, if I add 0 0, the carry and the sum, so there it's an half adder is an 2 input module with the 2 output modules. Okay, so it will be 0 0 and carry will be 0 and sum will be 0. So there are 2 independent outputs and both functions of A and B. So I have 0 1, so sum will be 1, 1 0 for which the sum will be 1, and for 1 1 the sum will be 0 and carry will be 1. Okay, so this is what is the half adder truth table looks like. So if I try to map it into a K map table, then I can have this is the sum, right? So x y bar, so this becomes an right y bar x, okay, because it is 0 here, and 1 0 becomes x bar y, right? So similarly the carry is just an x y. So if I have to implement these two in hardware, so I can write sum is equal to, because they cannot be paired, they are not adjacent, so I need to write separate expressions, x y bar plus x bar y, which can be further simplified and written as x or y, right? And carry is simple AND operation of x and y. So this is how an half adder looks like. So hardware wise, this is how it is going to be implemented, right? An XOR gate and this is the half sum and this is the carry out. Excuse me, HS means half sum. There is no carry in which is permitted in this particular hardware. Okay, there is no provision for carry in, only 2 bits. It can handle only 2 input bits. Okay, excuse me. So this is what an half adder looks like. Now if I say the delay aspect, if I see the delay aspect, I can say it is a 1 gate delay. So the output comes out to be carry, and the sum comes after 1 gate delay. Okay, so 1 AND delay for carry out and 1 XOR delay for the half sum. Okay, so these are the delay for the half adder. Now if I have to make a full adder, although this is an inefficient way of doing it, but still because 2 half adder, there is some modularity there, and that is why we are discussing this particular topology. So in a full adder, there is an A, B and C. Okay, so there are C incoming from the previous stage also. So if you see that from the truth table, so if there, so we know that for a sum, at least if there is only a single one or there are 3 ones, then the sum output has to be 1, right? So so we can just do 2 half adders, place 2 half adders, take the sum from the first adder and then put the carry in there, so you get the sum total. So this will become C XOR C in XOR A XOR B. Okay, so this is way sum can be straight away implemented. And now for the carry out, what we can do is, okay, this is like for the carry out, if in case any 2 bits are 1, then the carry out will be high, right? So I take an AB common, so I can write an C in into A plus B. Now if you see this A plus B, A, that is A or B, can be written as A XOR B and AB, right? So A or B has got 3 conditions, right? Other than 0 0, 0 1, 1 0 and 1 1, all the 3 conditions are there here. So the same thing is A XOR B. If I write, there are 2 conditions, A B is the 1 conditions. Okay, so the advantage of writing like this is, if you open the bracket, you will get C in A XOR B, and since A XOR B we have already implemented here for the sum, so we can use that out here, right? So that is the advantage of writing this in this particular format, right? So if you see here C in, I take again AB here common here, so this would turn out to be just AB plus C in A XOR B. Okay, so this is how this expression has been written in a simplified manner out here, right? So so if you write it in the simplified manner, then you can use the existing sum which is generated already from the previous stage. Right, so A XOR B is the sum, so that is being used out here to generate the carry. Okay, so the problem with this particular topology is, if you see here, the carry has got the a large delay. So generally this topology is not used. If you see here, 1 gate delay, 2 gate delay, 3 gate delay. So whereas sum is just 2 gate delays. But whereas carry needs to be propagated to the next stage, right? So this is not a very efficient way of implementing a full adder. So if I have to add, say, 4 bits, like once we have implemented an full adder, if I have to implement an 4-bit adder, all that I need to do is cascade it like this, and then take the carry from the LSB and give it to the next significant bit, and carry which is coming from this stage as an input to the next stage, and finally in the MSB you take a carry from the previous stage. Okay, so this once you do this cascading, you can add 4 bits, right? A0 B0, if you add, it will give you the sum 0 out here. A carry in also can come from the previous operations, so it will generate a carry out, and then that becomes an input to the next full adder. So A1 B1, and you add C0, you get an S1 and C1, and then you add A2 B2 and C1, and this is another full adder S2. C2 gets generated here, and A3 B3 and S3 and C3. So you are adding 2 4-bit datas, you are getting a 4-bit sum output, and also the overall carry. These are internal to the structure. This is the final carry which will be available. So the final output will be an 5-bit data. Okay, so you need to remember this structure, because in the lab portion we are going to implement this today. So I am going to give you a small demo, and then you will be able to implement this particular structure. Okay, okay. Now if you see the delay of this full adder, you could say there are 1, 2, 3, 4 adders and a 4 into full adder delay, because finally this output has to come, right? So this output depends on the input which is coming from here, and this again depends on the input which is coming here. So if you see the delay, this has to get generated, then this adder has to take this into consideration and compute and give a fresh output here. That will give an output here. So the total delay, if you see, the carry has to propagate through and through all the 4 modules. Okay, so it is 4 into full adder delay, and from the last slide we saw the carry is 3 gate delays. So that's why 4 into 3 becomes 12 gate delays. Is it okay? How did we get 12 gate delays for this ripple carry adder? Yeah, Tej, Sahana, anybody? Rajni, is it clear till here? Yeah, let me unmute also. If somebody wants to speak up, no, you can always use, otherwise you can use the chat box. Okay, thank you. Now if you see here, to reduce the delays in this ripple carry adder, so we have a better architecture which is known as carry look ahead adder. Okay, so here also you are giving 3 inputs, A, B, C, right? This is the C in which is coming, and this is generating 3 outputs. Okay, one is the sum output, okay, which is same as that of an full adder which saw last time. It is just an XOR gate out here, right? actually there are two XOR gates, right? So if you see A B, so once you do A B, you get an something known as propagation. So why do we call this propagation also? I'll just let you know. And then you have AB, which means generate. Okay, generate means you are generating the carry straight away, right? If A and B both are 1, then obviously there will be carry. So right, A, B are 1 means carry has to be there. So you are straight away telling the carry to be generated. Whereas propagate means, okay, if A and B only one of them is 1, right? XOR will give an output only when one of them is 1. So if only one of them is 1, that means you propagate the carry. Propagate the carry means in case carry is 1, right? In case carry is 1, okay, then the carry has to be generated. That means once you generate the propagate, then you will have to check what is C, right? If C is 1, then the carry will be 1, right? So this is just telling, okay, one of the one among AB is 1. And now if carry has to be 1, you please check what is the third input. Okay, that means it is just propagating the carry. So this is known as P, propagate. And sum is, like we said, 2 XOR, right? If you see here, sum is 2 XOR gates, right? A, B and then C. So that is what has been done here also. A, B comes as P, again you put it B here, C. So sum remains the same. Okay, we are only trying to optimize the carry path, because carry is going to create the delays in the circuit. Okay, now so if you see here, now I have A0 B0, so I have the propagate coming out here. A0 B0, this is the generate which is coming here. And this propagate comes here, and C0 also is coming here. These are the three inputs, A0, B0 and C0. So this generates the sum. Now how is a carry generated? You see this structure out here, right? So it is this two structure appears to be much complicated than what we saw a full adder, but there is distinct advantages which we will see very soon. So if you see here, if A and B both are 1, then the generate will be high. So generate will be high. So from this XOR gate, straight away I get a carry. Okay, after 1 gate delay. Okay, I can say after 2 gate delays, 1 gate delay here, 1 gate delay. Within 2 gate delays, I will get the carry output out here, right? Now suppose now only one of them is 1, then the generate will not be generated. Okay, only one of them is 1, right? So if only one of them is 1, in that case A0 B0 will generate a propagate. Okay, and then if only one of them is 1 and carry is also 1, then there will be 1 here, and that 1 through an OR gate will be available here, right? So you will have a 1 gate delay, 2 gate delay. In 3 gate delays, I will get the carry out here. So if I see, I can write the expression for carry as G0, that is generate 0 plus P0, propagate 0 plus carry 0. Okay, so is this block understood by all of you? Yeah, Damodaran, is that okay? Okay, so this is how an carry look ahead adder basic block looks like. Okay, so if I now see, I have this is the first bit which I have done. This is the block which I have done, right? Now for this block, okay, and for this block again I can write, right? This was an for the first block, right? And C1 was generated. C1 is coming as an input out here, right? Now the carry for this can be like if A1 and B1 is there, straight away generate signal can be generated from this block also, from the second block generate. And then if I have only one of them being 1, right? If both are zeros, obviously there is no carry. If only one of them is 1, then I have this propagate, and then if the carry is to be generated, that depends on C1, which is coming from this stage, from the previous stage, right? From the previous stage, the carry is coming here. So I can write as P1 C1, right? Now we saw C1 itself. In the previous case, we had written it as G0 plus P0 C0, right? So now if I substitute it as G0, which is generate 0 plus P0 C0, so this becomes the expression. So you have G1 plus propagation into G0 plus propagation 1 into propagation 2. So this is an AND gate, and C0. Okay. So what does this expression say? That okay, from this stage, okay, if both are 1, then I generate it straight away. I don't have to bother what is the incoming, right? Because if both are 1, carry is to be generated. Doesn't matter if see what is coming from the previous stage is 1 or 0. Okay, so I have G1. Or if only, say for a case only if either A1 or B1 is 1, okay, in that case, if there is a generate from the previous signal, okay, that means carry will be there. So straight away I generate the carry. Or if only one of them is 1, and here also only one of them is 1, right, then if this carry is 1, then it will get propagated from this to this. So this is the expression. That is why we call it as propagate signal. Okay, so this is the expression for the carry from this block. Okay, now hardware wise, if I want to implement this aspect, so I can do this. Okay, so this is like generate 1, okay, through a OR, carry 1 is coming straight away. That is one condition, right? And then this is P0, that is propagation from here, and the C in C0 here, one AND gate, C1 is coming. So it is like the maximum delay, I can call it here as 3 gate delays. Okay, 2 gate is seen here. Okay, the third gate is this P0 also will take 1 gate delay. So I can say 3 gate delay, C1 will be generated. What about C2, right? And if you C2, you see it's an OR gate out here from this expression, G1. So G1 will take 1 gate delay. So 1 plus 1, 2 gate delays. This in this path will have 2 gate delays. What about this path? If you see here, propagate 1, and there is a generate from the previous stage. So I have this here. So this is 1 gate delay, 2 gate delay, 3 gate delay. C2 will be available here. And there is a third condition where this is also propagate, this is also propagate, and then you have an carry in which is coming from the first stage itself. So you see C1 and C2 both have only 3 gate delays. Okay. So obviously the hardware has increased now, but then if you see both C1 and C2 both have only 3 gate delays. Is this okay, all of you? Now if there is an issue, let me know, we can discuss it once more. Is it clear, Naveen, Maunika? Okay. So if you have a doubt, you need to tell me, so that we can discuss it again once again. So if you see here, I can this expression which we wrote, now I can expand it to 4 carries also. I can write C3 is G2, just expanding it with one more variable. So this becomes G2 plus P2 G1. Okay, that is now if I if it is both the bits are 1, then obviously carry will be generated. But if only 1 is there, then from the previous stage, if there is a generate, okay, or if there is 2 propagates and generate from the previous stage. So this is how I expand these equations, okay, for 4 carry. Now if I try to implement this, this is how it is going to look like, an 4-bit and the carry look ahead adder. Okay, now these we discussed. For the last one also, if you see here, okay, this is generate, right? That means if B3 and A3 both are 1, straight away carry will be generated. That means within 2 gate delays it will be generated. Okay, otherwise if it is a propagate here, if it is a propagate here, it is a propagate here, it is a propagate here, then depending on C in, right? So if you see here, this propagate is put here, this propagate is put here, and this propagate also is put here, this propagate also is put here. So it is all propagates have been put here, and you have an C in coming here. Sorry, this is the one. Okay, all the propagates have been put here, and C0 also has been put in here. So if you see here in this, Also, what is the delay? It is all the propagates will be generated within one gate delay. So 2 gate delay, 3 gate delay. So even for an 4-bit carry look ahead adder, the total delay is only 3 gate delays. So that is the great advantage what we have. Okay, so if you see here, so it has got only 4 gate delays, right? So whereas when we saw here previously, here we had 12 gate delays. Okay, here we just have the carry being generated with 4 gate delays. So obviously this is 4 times faster, you can say. Okay, the only penalty which you have to pay is increased hardware. Okay, so always there is going to be some penalty. So this operates much faster, but then it consumes more area and more power because the number of gates used here is larger. So you can say they are all doing parallel processing. Okay, so that is the reason you have a larger number of gates. Okay, so but the delay is reduced significantly, right? So you can see here almost it is 4 times faster. Okay, this advantage will be amplified further if you try to do an 8-bit adder. Okay, now 8-bit adder, this particular hardware, if you keep expanding, then it will require it will consume much larger area, right? You have an 4 input AND gate here, then 5 input AND gate, and a 6 input AND gate. They'll cause lot of hardware penalty and delay penalty also. So rather than doing that, you can have a one 4-bit CLA and the second 4-bit CLA. Now you take this carry here and feed it here as an input. Okay, so there will be 3 gate delays for this block, and you are giving it as an input here, so you will get it as 3 again another 3. So the total delay will be each CLA block is going to give me 3 gate delays. Now for an 8-bit it will be just 6 gate delays. Okay, this should be 2 into 3 delay gate delay. Okay, let me change that. It will be 6 gate delay. Okay, whereas if I go for a conventional design, if I go for a ripple carry adder, right, it will be 8 into 3 gate delays, that is 24 gate delays, right? Because you're just cascading here like this. The carry has to propagate from all these 8 stages. So 24 gate delays, whereas here it is in the previous stage we saw it is only 6 gate delays. So if you have an n-bit adder, right, here it will be n into 3, whereas there it will be in this case it will be every 4-bit will generate only 3 gate delays. So n divided by 4 and into 3. So you find this particular structure, okay, ensures that the propagation delay is very less. So this is what is known as carry look ahead adder. Okay, you could also have a serial adder which is based on registers. Okay, it's an clock circuit. If you see here, this hardware requirement is just 2 registers and 1 single full adder. Okay, so this is just for an 4-bit adder. If it's an 8-bit adder, nothing changes, but this size of the register changes, that's all. Now, otherwise there is requirement of only 1 full adder. So what is done here is, if you see here, initially the data is fed here, which requires to be added. So you have x0 and y0. Say the full adder is initially clear, so it adds x0 and y0, right? So the sum is available here, right? and the sum will be available here. Okay, initially say this is also no, reset to 0, so 0, it's a 0 here, so it is just adding x0 y0 and the sum is available here. So during the positive edge of the clock, what happens is this sum is fed here. This is serial shift register. Okay, so it is going to shift the entire data towards the right. Okay, so in the first clock cycle, this sum which was generated and gets loaded into this register out here. Okay, into x3 and then x0. Right, and the position of x0 is now taken by x1, and y1 comes into the y0 position, and also this y0 is fed back here, right? Okay, so and then what happens is during the positive edge of the clock, again this carry which was generated in the previous stage, that will be captured by this flip-flop, and then you add now the now x1, y1 and the carry. Okay, then the new sum will be generated and the new carry will be generated here. Now in the next clock, again that new sum which is generated, that will be pushed in from the left hand side, and the entire data will move towards the right. So at the end of now 4 clock cycles, what would happen is the sums which have been generated, okay, that will come here. Okay, all the 4 sums will be coming here. A carry will be available here, and this will get restored with the previous data. But because y0 again it will come here, again y2. So if I do a plus b, the contents of B register will remain the same after 4 clock cycles, right? And in A, the sum of like you might have seen how it is done in 8086. If you write and add A plus B, then the contents of B remains there, and whatever is the contents of A gets modified with the sum of A plus B. So that is what exactly happens in this block diagram, right? So this is a better architecture. So you see now we are discussing, we discussed one architecture here. This was it requires lesser hardware, but there is no clock and all required. This is just a pure combinational. Then we learnt about an improved architecture out here, which has got a greater much lesser propagation delays, but then the hardware requirement is up. In both these they are pure combinational, so there is no clock requirement out here. Then we said we have something like this, and this is an synchronous counter where a clock is required here. In this, the hardware is totally brought down. We are just using a single full adder. Okay, so these are all various kind of architectures for an adder. Okay. So you can also have an adder subtractor. Okay, because in the next class we are going to see a design of ALUs and all. So let's just, this is the basic block of an adder subtractor. So if you see here, if this is an example of an 4-bit adder subtractor. So if a 4-bit data, right, if I have an 4-bit data, right, that it can represent actually from 7 to -8. Okay, so in 2's complement format. Okay, so like 0 0 is 0, and this is 1 2 3 4 5 6 7, and 8 is not represented, right, because the 8 becomes 1 here, and that is actually -8. Right, and how did we get 2's complement out here? Like suppose this is 1 0 0 0 0 1, right? To get 2's complement, what do I do? Right, if you remember from your digital design classes, for 2's complement, I write 1 1 1 0 and then add 1. Okay, for 1's complement you just invert all the bits. For 2's complement you invert all the bits and add 1, right? So if I invert all this 1 1 1 and 0 and then add 1, it will become 1 1 1 1. So -1 is 1 1 1 1. Okay, similarly if I go to 7, it is 0 or 1 1 1. right? So this is if I invert it, it will become 1 0 0 0, and then if I add 1, it will become 1 0 0 1. So minus 7 is represented as 0 1 1 1, and 1 is represented by 1 0 0. So here the first bit out here, if you see here in the 2's complement number, the first bit indicates the sign, okay, right, and minus 8 is represented here. Now if I take the inversion of this, it will become 0 1 1 1, and if I add 1, it will become 1 0 0 0. So it is like a plus 8. So this is minus 8. Remember here plus 8 cannot be represented if I because I am talking about only 4 bits. Okay, when I take only 4 bits in 2's complement method, the range which is of numbers which can be represented is from plus 7 to minus 8. Okay, is this okay? Yeah, Maria, Tej, is it okay? Yeah, it would be nice if you keep telling us or no in the chat box, so I'll know that I'm at an okay pace. If you have doubts, please let me know. Okay, now if you see here, let's take some examples out here. Okay, now how is this in a full adder implemented, adder subtractor? Okay, now I have A0, B0, so this is the control line which is coming. Okay, now what does the control line do is, if m is equal to 0, okay, if m is equal to 0, I have A0 coming here. So in an XOR gate, if you see, if one input is 0, what is the output? It will be B0, right? If XOR gate, what it does is, I have 0 here, if it is 0 here, it will give 0. If I have 0 here, if I have 1 here, it will give 1. That means an XOR gate will just be transparent in case I give one of the inputs as 0. So whatever is the other input, that simply passes through, right? Okay. Why? Again, let me explain it once more. If in the XOR gate, if one input is 0 out here, right? If it is 0 here, 0 0 will produce 0, and if it is 1 here, 0 1 will produce 1 here. So that means if m is equal to 0, all these gates will become transparent. So I have A0, B0, A1, B1, A2, B2, and A3, B3. So this will add these data as it is, right? Now and carry in also, you are giving it 0. Suppose I have to do an subtraction of these two, then I give m is equal to 1. So this is the control signal which will tell this particular adder, okay, now these two data needs to be subtracted. So you need to subtract b from a. So I give m is equal to 1. So the moment I give m is equal to 1, what these XOR gates are going to do is, like if it is 1 here, if B0 is 0, so 0 1 will give 1, right? And if it is 1 here, 1 1 will give 0. So it is going to invert these datas. So if you see here, when I give m is equal to 1, it is going to invert B0, B1, B2, B3, right? And what is 2's complement? 2's complement is nothing but you invert it and then add 1, right? So when I put m is equal to 1, it will invert all the 4 bits, and then I need to add 1 also. And for that reason, from m I have taken a signal and given it in here as C0. So that add 1 thing will be done through here, right? So now what is it? When I am giving m is equal to 1, what I am doing is, I am taking the 2's complement of b. Okay, I have inverted everything and added 1 here, and then adding it with b. So the net result will be a minus b here, because I am adding 2's complement of b with a, so it will do a subtraction, and that is why it is known as adder subtractor. Okay, now if you see here, in this case, there is something known as an overflow also. Now let's take an example. This is 4. Okay, and I am adding minus 3. So from here, minus 3 is 1 1 0 1. I am adding it. So 0 plus 1 1 0 1. So the net result is 1. There is a carry out which is generated, which we should neglect. Okay, that is what in 2's complement we do. If there is a carry which is generated, we just neglect it. Okay, now if I take one more example out here, minus 4 and minus 5. So this is minus 4 and minus 5. If I do the addition, right, the answer is 0 1 1 1, which is 7. Obviously this is wrong, right? So this is not 7. right? Minus 4 minus 5 is so that means minus 4 and minus 5 if you add, it is minus 9, and minus 9 is out of our range. So this is an overflow condition. Okay, this is an overflow condition, and that is why this answer is wrong. So this answer is wrong out here. Okay, now this doesn't know, like we have to tell how to say this is wrong. So we need to program it or make an hardware which detects this kind of overflow. Now I take one more example, minus 8 and 4, right? So this is a minus 8, and then I do an 4. So what is the answer I am getting? 1100. So 1100 is minus 4. Okay, so this is also an okay, this is also a valid data, so no problem here. Now if you see here, 4 plus 4, again 4 plus 4 cannot be represented in a 4-bit and a 2's complement system, right? So 4 plus 4 will give a 1000, which is minus 8 actually. So this is also an wrong answer. So if you see here, if I just look at only the carry, then I cannot say whether overflow, because here there is no overflow, there is an overflow here. There is no overflow here, there is an overflow here. So just looking at the carry, I cannot say. But if I look at this carry and do an XOR with the carry from the previous stage, here if you see here, 1 plus 1, right? 1 plus 1, it will generate a carry here. Again 1 plus 1 is generating. So if I do an XOR of this carry and this carry, it will be 0. That means it's a valid data. So right, so I take an XOR here and an XOR here. If it is a 0, then means it is and valid data. Okay, so now here if you see here, here it is 1 plus 1 carry, 0 and 1 there is no carry, right? So if I take this carry and this, so there is 1 carry here, there is no carry here. So if I do an XOR, there will be a 1 out here. That means there is an overflow condition. So it will detect the overflow here. Similarly here there is no overflow, right? 0 plus 1 is 1, 0 plus 1, so it is 0 0, so it will, the output is 0. That means it is valid. So from here, if it is 0, it is valid. Okay, so that is what here if you see here, 1 plus 1 there is a carry, and here there is no carry. So 1 carry and no carry will generate a 1. So the output out here will be overflow. Okay, in some textbooks it's written as V, which is actually a wrong notation. It is actually V bar. That means a valid bar. Okay, it is an overflow. Whenever there is a 1 here, it means it is overflow. Whenever it is 0, it means it is valid. Okay, so this is how we design an 4-bit adder subtractor. Okay, so now we can do a binary multiplier also. So how do we make a multiplier? You have 2 into 3. If you do like what you first take the first digit, and then you multiply with this, and then you do shift it and do it. So the same thing is done in the binary also, right? So you take the first one, you do 1 0, and then you take 1 and you do 1 0, right? So you get the same thing, right? So here only thing is to remember, like A0 B0 when we multiply, okay, there's only 2 possible conditions, right? And okay, A0 0 and 1 and 0 and 1, right here. So if you multiply 0 and 1, okay, this will be 0, right? And 0 0 will be 0, 1 1 will be 1. So simply A0 B0 can be realized by using an AND gate. So 1-bit multiplier, okay, only 1-bit multiplier can be simply realized by using an simple AND gate. Okay, so so 1-bit, this is the truth table for 1-bit. So you can simply implement using an AND gate. Okay, now let's take, if I have to implement an 2-bit adder, then what we need to do is like A0 B0, you multiply, you get A0 B0. So I have put an AND gate here. Okay, B0 and A0, I get the first product, partial product. Then here I have A0 B1. So A0 B1, another AND gate, and I use an half adder. So, and then what needs to be added? B0 A1. So another AND gate, B0 A1 and half adder. So once I get the second partial product, and there could be a carry which is generated here. So I take this carry out here to the half adder of the next stage, and then A1 B1. and then I have B1 A1 here, and the carry whatever is being generated here. If I do that, and if both are 1, then there could be an carry here, so that carry becomes as the partial product 3, most significant bit, and the sum comes at as P2. Okay, so this is how a binary multiplier 2-bit and 2-bit looks like. Okay, now in case I have to do an 4-bit into 4-bit, okay, now the same logic can be extended further, right? So like this is what A0 B0, and first I take and multiply it with by 4, and then shift it towards the right. Second bit I take and multiply it with by 4, and then keep shifting. This is how normally it's done, right? So that is what has been done here. So A0 B0, the first one here, A0 B0 comes as it is, right? The next one is A0 B1 and A1 B0. So A0 B1 and A1 B0. So you have an half adder, only two. Okay, this A0 B0 actually represents an AND gate. Okay, so all these that AND gate is not shown here. So A0 B0 will be generated through an AND gate. A0 B1, A1 B1, all these will be generated through an AND gate. So you put an half adder, and it generates an carry out here, right? So now here in the third one, I have one carry which is coming here, and there are 3 more this to be added, right? So I have A0 B2, A1 B1, right? Here A0 B2, A1 B1, and A2 B2 is left over. I have taken this as an full adder, so I have taken this carry which is being generated from the previous stage, and then I have put in A2 B0 also here. So again, right? So this sum which is coming here, again you have A2 B0. So I can use a half adder here, so I get an product here. Okay, so I can expand this further, right? I take this out here. Now here if you see A0 B3, A1 B2, and this is a carry which is generated from here, right? Okay, so that is taken here. A carry could be generated here also, that also needs to be taken care of. So I put here, this sum is coming here, and then I have A2 B1 also here, then A3 B0 also requires to be added. So I have an A3 B here. So carry could be generated in one of these adders. So both have been taken care of here. So I have an next product coming out here, right? And then if you see here, after that it is A1 B3, A2 B2. I use a full adder. This carry is taken care of here, right? And then I have A3 B1. This carry is been taken care of here, and then you could have a carry coming from here. So now here all the 3 terms have been taken care of, so I can use an half adder. So this sum comes here, this carry comes here, so I have product 4 coming here. This carry is again taken here. Now here if you see, there are only 2 terms, so I use a full adder. This carry is fed here, right? And this carry is fed here, and this is, I can use a full adder. I can straight away take this half adder carry here, so it will add all these 3, P5. And similarly the last one is an A3 B3, and the carries which are coming from these stages. So this is how an 4 into 4 binary multiplier can be implemented using a full adder. So if you see the delays out here, the worst case delays is 1 half adder, 1 full adder, 1 half adder, okay, or a half adder, full adder, full adder, full adder, right? And then full adder, another half adder, then full adder, then full adder. So you 1 2 3 4 5 6 around close to 7 adder delays are there in this multiplier. So that is the kind of delay which will be experienced here. And also the hardware requirement, if you see here, it requires a lot of hardware. Okay, so this is just for an 4-bit. If you expand it to 8-bit, you can imagine how many full adders and half adders will be required. So it consumes a lot of area, and the delay is also very large. So something more efficient way of implementing an adder will be using something known as Booth algorithm. Okay, now if you see here, what is done in a Booth algorithm is, this is the bit, right? If you are multiplying it with a, if this is 0, what is we are writing entire thing as 0, and then shifting it towards the left, okay, or and I can say you are shifting it towards the this, you are shifting it towards the right, okay. Similarly, this is 0, so I am writing it in all zeros. If it is 1, then B is written as it is, right? B is written as it is, and with every operation I can write the new operation is being shifted towards the left, or I can say the old operation or old result is being shifted towards the right, okay. Old, whatever was old, that is being shifted towards the right. And if it is 0, then right, it is everything is 0, it is 0 is added. If it is 1, then whatever is B, that is being added, okay. So that is how the Booth algorithm works like. Right now, hardware wise, it is very simple to implement this particular algorithm. If you see here, this is the multiplier, okay. This has been put here, okay, one data. The second data will be put in the multiplier, and initially this will be loaded with 0. This is the result which is there. So the accumulator, which will be all zeros, okay. The final answer will be available in A and Q together, okay. We'll see how that happens, okay. So if you see here, initially everything is 0 here, everything, this is the data which is available. So I am first checking what is the first bit, okay. This is the control sequence detector. So the first bit I am checking. If it is a 0 out here, right, this is a mux I am using, so I am going to add a 0. So initially it was 0, I am going to add 0 itself. So nothing, and then once it is added, I am going to put it into this shift register as it is, okay. So it is, I am going to load this data say into this register, okay. Then I am going to check the next bit, okay. Now if I am going to check the next bit, if it is say 0, I will again add 0. Suppose it is 1, then I will add the multiplicand, okay. So whenever and then again I am going to keep shifting this data towards the right, okay, every time. So what I am doing is I am doing exactly this, okay. If it is a 0, this A is here, A, right, sorry, it is available here, A, okay. If it is A is 0 out here, like if it is A is 0 here, I am putting all zeros here, right. So this is a mux, okay. 0 means if it is an if this is 0 here, this will be given, 0 will be given here. So this adder will add 0 with the previous data, right, okay. And if it is 1 out here, then it will add multiplicand is B, this data, right, this is being added. So whenever there is A is 1, you are adding B, right. So that is what exactly what is being what is happening here. So whenever it is 0, right, and it is adding 0, and if it is 1, it is adding this multiplicand, okay. Second thing what we need to do is, with every operation, okay, this data needs to be shifted towards the right, this data, whatever you have done, whatever you have added, needs to be shifted to the right. So I am using a shift register to shift the data towards the right, okay. It is serving two purpose. One, it is shifting, also it is pushing out the A data. So initially we have pushed A into this, right. So every time you are pushing out, so this will go automatically. We are looking at the last digit out here to decide this control signal, right. So automatically by pushing it right, the second purpose which is solved is, we are slowly moving from here to here, one bit we are taking. So both the purpose is being served here. So this is how at the end of if it is an n bit adder, after the end of 4 clock cycles, you will find the answer which is available in this register, okay. So this I can show you through two examples, then it will be pretty clear to all of you, right. Suppose this is M. So initially A will be 0, this will be 0. Here some data has been put. Okay, this is an Q0. So this is one which we are going to multiply. So this is which is being put here, right? And M is 0 0 1. So if you see here, this is 1 out here. Okay, so that means from the multiplexer I have now this data coming here. So so 1. So this data will be coming here. So this 1 will be added to the accumulator. Let's say let's again also assume that during the positive edge of the clock, this data will be loaded into this register, and during the negative edge of the clock, this data will be shifted towards the right. Okay, during the positive edge of the clock, because these are registers, like they are clock dependent. So during the positive edge of the clock, this data whatever is available from the adder will be loaded into this register, and during the negative edge of the clock, this will be shifted towards the right. Now if I take that during the positive edge of the clock, this is M. So M and A gets added, so I get 0 0 0 1. Okay, this is the first operation. In the negative edge of the clock, it will be shifted right. What will be shifted right? A and Q, right? M remains same. This remains same. Only here we have A, and this we have initially loaded with M. So this gets shifted. So now if you see here, this has got an A and Q. They have got shifted towards the right. So this 1 gets thrown away. So this 0 comes here, 1 here, 0. This 1 from here comes here, because they are in series. These are from here to here it is fed. So this 1 comes here, 1 here, and then from here, and 0 is pushed in from here. Okay, always 0 will be pushed in. So a 0 is pushed here. Now if you see here, now this is a 0 here, right? So 0 means again a 0 will be added here from here. So there won't be any change in the accumulator data. During the positive edge of the clock, this accumulator data will remain same, because this is 0, and hence only 0 will be added here. So this remains as it is. Okay, and during the negative edge of the clock, again this will be pushed towards the right. So I have this one coming here, this one coming here, 0 1. This 0 is pushed out. So I have a 1 out here, right? So this is 1 out here now in this case. And now if you see here, in the next positive edge of the clock, since this is 1 out here, obviously this will be added now in this case. So this is all zeros here, now 0 0 1 1. So I have a 0 0 1 1 out here, right? So I have this data being uploaded with the new data out here. In the next negative edge of the clock, this will be pushed towards the right. So I have 1, so 1 1 0 out here, right? Again next clock, it is a 0, again a 0 is added, nothing, accumulator doesn't change. And then negative of the clock, it is again the data is pushed out. So this is the, now if you see what is the final answer, the final answer will be together, which will be available in A and Q. Okay, so because you are adding 4-bit into 4-bit, you have to get an 8-bit data. So this will be available out here. Now if you see here, it is 1 1 1 1, which is 15. So 3 into 5, I get 15. Okay, so this is how an Booth's algorithm works like, right? So this is just one example. So we'll take an break out here.